Hey everyone, thanks for joining us for today's State of the Field series. My name is John Patinos. I'm a project manager at the C2 Smart Center, a US DOT designated Tier 1 UTC tasked with leveraging recent advances in big data and technology to solve today's most pressing urban mobility challenges. In the State of the Field series, we're aiming to bridge the gap between the best of research and the state of the practice, and we're going to share the latest advances, opportunities, predictions, research bottlenecks, what perspectives or skills are needed towards tackling one of the world's most pressing problems in transportation. So today I'm joined with my colleague, Professor Hani Nassif. Professor Nassif is a professor at Rutgers, where he's established the Bridge Engineering Program. His expertise includes structural health monitoring, SHM, and the application of Way in Motion, WIM technologies for monitoring trucks and their impact on the transportation system. We'll hear a lot about that today. Among his many accomplishments, Dr. Nassif has worked on pioneering work for the reliability-based code calibration of the AASHTO LRFD bridge design specifications, and many more. He's also a member of TRB, IEEE, ASCE, IABSE, and IABMAS. He's asked me to keep his bio short, so though I could go on, I think I'll just turn it over to him and we can get started on today's webinar.
Thank you, John. Good afternoon, everyone. Let me start by sharing the screen. And do you all see my screen?
Yep. You just have to put it in presentation. Perfect.
Okay. And I'll bring this here. Great. Thank you for the introduction, and thank you for the opportunity to present our work part of the C2 Smart testbed. I appreciate the series. I think on structural health monitoring, the first was by Eric Zucker from HNTB, who really presented the nice applications that HNTB has done in the region and other nation projects on the application of structural health monitoring. So what I wanted to highlight today in this series is how do we combine and that was out of necessity in most of the projects. How do we combine the structural health monitoring with the Way in Motion sensors, which is mainly used for assessment and evaluation of bridge structures in particular. So our group and the work that was done as part of the C2 Smart support. And, I would like to acknowledge my co-presenters, including Che Kokna, who's a research associate, Panglu, research associate also, and my doctoral students, Talis, Chan, and Sirap, as well as the contribution of my colleague, Professor Asbey, who's the director of the C2 Smart Center at NYU. We go back, Khan was at Rutgers and we did some of the work together, and now we're applying some of these projects into future endeavors. The structural health monitoring, as has been highlighted by many of my colleagues, is that it's becoming a useful tool for the bridge owners to really make a quantitative assessment, to be used for evaluation of existing bridges. And in particular now, there's a trend, and it started in Asian countries, in South Korea and China and Japan, where even new structures have been instrumented. And that trend has been also followed in the United States. A big example is what Eric Zucker from HNTB presented last time, which was the Tappan Zee Bridge, which had a major instrumentation program. The information is always very, very good in terms of the assessment, in terms of telling us how are these structures behaving, what are the changes that needed to be done for future designs, future codes. When we do use new material, carbon fiber or composites, how do they behave? How are these bridges different from other structures? And but in particular, especially for load rating, it gives us the code now. The manual of bridge evaluation allows the site-specific development of live load based on the Way in Motion data. So in other words, especially for bridge structures, the information from the load side using the WIM technology and the information from the resistance side, which is using the response of the bridge from the sensors, when they are coupled together, they can really provide a great insight on the service life prediction of these structures. And it's proven, it's quantitative, it's based on many probabilistic predictions, which are likely to be the case rather than having a huge maximum envelope that we use in the design. Before I want to continue, and I'm gonna, the way the presentation is made is really, it's case studies. We have, projects that our group, with the help of C2 Smart, we were able to implement this combination of what we call SHIM and WIM, the structural health modeling and the way in motion, and how the value from each segment of the instrumentation was be able to fuse together to be able to tell the story about what are the future predictions or future behavior of these bridges. Well, what is the role of structural health modeling is that, perhaps many failures or many causes of failure could have been interpreted much better, if we were given the opportunity to have sensors placed prior to the failure of these bridges. Perhaps we could have had some warning about an impending failure and therefore avoid that situation. We will never know, but I think now the lessons learned are that if we had sensors on those structures, we probably could have avoided these disasters. I just want to share with you this video. I don't hear the voice, but this is the pictures coming from the I-35 bridge in Minnesota. This is the instant of failure, and if we had sensors on those structures, and I think the report came out, it's a design shortcoming of the gusset plate, but at the same time, there were some exceptional loads were loaded on the structures. I think they were boulders and aggregate. And if we had those sensors for a while, we could have interpreted this, type of failure or type of, behavior, prior to something happening. But I want to emphasize now, so what the idea that the trucks, the overweight trucks, especially on everyday bridges, the ones that we use every day, there is an impact of this overweight over time. And it could be fatigue, it could be accumulated damage, it could be cracking, it could be many reasons that can be initiated by an overweight truck. And it's enough for one truck to do damage, and then the repeated loading of that could lead to excessive loss of service life. And instead of we design it for 75 years, we might end up getting 50 years or 40 years even lifetime from the structures. So what I'm highlighting on this slide is the trends. And you can see we did some way of motion data for probably 20 years, and we're seeing that there is an increase in the maximum loaded trucks. So in other words, although if you look at the average, the mean value of the over 10 years, and by the way, we did also 10 more years of the same site, and you can see the trend is the same. So that means the 95th percentile of the trucks are increasing, and that rate of increase is alarming. Though it's small, but it's alarming. At the same time, we looked at the ADTT in general, and you can see it. This is from a New Jersey DOT WIM data that they had available, and they have about 84 WIM sites in the whole state. And we tried to compare how one of the bridges in the vicinity of those data is going down. You can see the dotted line, the rating, over the years, and how the ADTT is increasing. So that means, of course, there are some years where this is the economic downturn. You can see it going down, but the trend overall is increasing. That means probably we're issuing more permits. Probably there are more overweight trucks. But the thing that I noticed, we took data from the weigh station, that the effectiveness of the enforcement, trying to curb the overweight trucks, is really very limited. So the weigh stations, this is some data, although it's a little bit old, but it's revealing about the magnitude that we don't really, the weigh stations in the side of the highway, the roadway, they're not really very effective in capturing these overweight trucks. And you talk like about only 0.5% are caught on these weigh stations. So the modus operandi of trying to look at the overweight trucks and enforce that weight limits is not really effective the way it's done. And so we need to have a new ways, and this is one of the motivation for our work at C2Smart. We are taking the lead on trying to put some automated enforcement, or what's referred to as direct enforcement, whereby you would weigh the trucks with very high accurate sensors, and with a camera you could get the license plate, and then you would be issuing a citation based on that technology. I think that's getting some grounds, and many countries have been starting to use that technology over the last 5 years. And we have an initiative with the New York State DOT, who is now leading, I would say, in the nation, to try to implement such technology and make use of it on one of the most important sites in the city for measuring what is the impact of overweight trucks. So I'll talk about that as one of the case studies. So what I wanted to highlight is about 5 case studies that I selected, and I'm going to go through them quickly to show the effectiveness, how we were able to solve some puzzles by combining what are the loads and what are the response of the bridges, and then try to figure out what is the issue and then provide a solution for the agencies. So why do we have to do both, this combination? Well, it's much easier than when I started, 25 years ago. Storage of data was a problem. I mean, storage was very expensive. Computing was very, very limited. Luckily for our field, now all of that became very, very cost effective, and the computing power, the wireless technologies allows us to really collect data and from our office sit and do what we used to do over a year. We are now doing it almost in one day. So I think the fast-paced improvement in the computing power and the wireless technology and the storage helped us really make this a very viable option. And we are implementing many of those, as you will see. And what do we do with that data? Inspections are important, right? But it doesn't really reveal everything. So we need to have sensors, and I'm advocating not on every bridge, but at least on a population of bridges that can be representative of the bridge stock in our database. And then using the models, using the predictions, then we can have some idea about when is the maintenance needed, rather than doing it periodically every 2 years. Some bridges, they might not need to be inspected every 2 years. So these sensors can give us a little bit more information about the period that can be done, and therefore, reduce the cost of maintaining these bridges. I just want to, I think Eric last time shown a lot of the technologies that they have used. I just want to quickly highlight some of the sensors that we've worked with, over the time, including vibrating wires, strain gauges, strain transducers. These are shown here in the picture here. If you can see, my mouth is BDIs, Bridge Diagnostics, very effective strain transducers that give very good data. Some accelerometers, this is from a project, some wireless accelerometers that now we are using more. We don't need the cabling. It's really half of the effort was in trying to lay down the cabling and try to get the data that way. So that was a limitation. Now for long span bridges, we're able to put sensors and they're wirelessly connected. So they're very effective in that way. And in the weigh in motion side, there are mainly many types of sensors, but I would limit those into probably 3 types. One of them is what we refer to in the upper left corner here, is the piezoelectric. sensors, the referred to the polyvinyl PVDF type of sensor. Those are what the majority of the Department of Transportation are using because of the low cost. However, their accuracy is not very high. So if you want to use them for enforcement, they are within 10% accuracy on the gross vehicle weight. This is according to the ASTM standard. And the load cells and the bending plate, those are kind of, I don't want to say older technologies, but their technologies I worked with one on the Remus Avenue Bridge about 23 years ago. And it was effective. It was very good to use, and the accuracy is very good. However, it's mechanical and it's really demanding a lot of effort on the infrastructure below it. Meaning, in the approach slab, it has to be, you have to have a drainage, and so it's really very involved, and it needs to be maintained every year. And the last sensor that we are really currently now in partnership with our industrial partner and Citosmart, a company located in New York also and all over the United States, Kistler. They have produced the top of the line sensors, I would say, the pairs of quartz. And those are pressure sensors, and they're very effective, very highly accurate, and they are encased in an encasement, so they're independent of temperature. The other piezoelectric, they will drift. They depend on the temperature of the pavement, which also fluctuates on a daily basis and on seasonal variation. So those sensors, the advantage of them are they have a very low noise to signal ratio, and they are not impacted by temperature. And so we've used those extensively now, and this is the one that we are proposing to do the enforcement. And one of the case studies that I started with, and I want to here, I think I always put the NJDOT, and those I want to thank all the support I got from NJDOT when I was an assistant professor. This was the best help I could get to my career, that they were very open to really doing future ideas. And so this was the first bridge, for those of you who might not be familiar with what the Remus Avenue, why is it special? It was the first LRFD designed, and this was, LRFD was out in 1994, and in 1998, when I joined Rutgers, I think the dialogue started with the bridge engineers at DOT at that time, and the vision was, let's move to LRFD, and then this was the first bridge that was designed by, at the time, Parsons Brinckerhoff, and we worked with them very closely in trying to implement and to implement this sexual health monitoring system, to learn about how is the AASHTO LRFD code behaving in terms of the key points in the code. How are, especially the ones that were not validated, like the fatigue models, the distribution factors, the impact factors, all of these aspects, they were addressed in this project. And what happened there is we put a the bending plate system so that we can get an idea about the load side. And this was the entrance to the portway in Elizabethport. And the expectation at the time was that this port is going to be receiving about 15,000 trucks a day. I think at that time it was about 5,000 to 6,000 trucks a day. So that was an idea to monitor that. We also looked at putting sensors, different kinds of sensors, including one of the objectives, for example, was to monitor what is the deflection limit. Many states were, foregoing the deflection limit. They're saying we don't need them. They don't. Whereas the DOT, until now, they still have that deflection limit on some of the span. And it's a good idea to learn how is that limit that was imposed is changing the design or even the limitations on the designs. So for that one, we did a very extensive, before the bridge was open to traffic, we did a lot of testing, static and dynamic, and we did some of the modeling. and we were able to develop some of the simplification of the distribution factors. At the time, the equations that were in the code, they were perceived that they need a little bit of iterative and complicated. And we were able to do the impact, dynamic impact, some models for that, fatigue prediction models. But one of the things that came out of that project is that we also tested a new design for the bridge approach slabs. That was a problem because it was cracking the design for about 40 years. The DOT was using the same design, but they wanted to move to a better design and to minimize the cracking. So we did a complete modeling for it, the 3D model, and we put all kinds of sensors, including pressure sensors, settlement sensors, and we were able to predict when does it crack. This is almost, we did about maybe 2 years of monitoring, and after about 160 days, we were able to pick on the sensor the crack, and we observed the crack location. So without those, we wouldn't have known when it would be cracking. So you could see after 100 days, and after the bridge was open to traffic, the strain the tension started going up. And this is the concrete. We had some capacity of the concrete to cracking, and then we were able to predict that there will be crack here. And from the crack mapping on the site, we were able to confirm that. So the design to resist that, we came up with a really nice design, which is almost like a waffle slab, and we stiffened the plate by adding some beams. And I think this is the detail. Perhaps it changed a little bit over time at DOT, but it's still and we increased the thickness. The thickness was, instead I think it was 12 inches, now it's about 18 inches. And that has shown to be very effective in mitigating or eliminating the cracking in the approach slab. So that's one of the outcome of that project. Another project that we did where we used both of them successfully was with the turnpike. And this is the Delaware River Bridge, which is the one connecting Pennsylvania with New Jersey. And in that one, the concrete was being poured. It's about 6 lanes. So they pour concrete in 2 lanes, and then they have 4 other lanes, 2 lanes in each direction for traffic. But when they were pouring concrete in the 2 lanes, the two traffic lanes were open to traffic. And they were observing that there were a lot of cracks being, after they cured the concrete for 14 days, they revealed the covers, and they find out that they had a lot of cracking in the concrete. And I think at that time, the discussion, because our group has wrote the HPC specification, right away, everybody was pointing towards as a shrinkage cracks. However, the cracks were really every 2 feet. And and when the Turnpike Authority asked me to look into this, I said, it cannot be shrinkage cracks, because once you have a crack every 2 feet, it sounds like it's something else. So let me try to, when they pour, next pour, let me try to figure it out. So we did some modeling, and we put some sensors, and including, as you see in the middle here, some portable sensors. We have a portable unit that you see it here behind the barrier. And we measured the truck weights in the travel lanes. And we had all kinds of sensors embedded within the concrete. Even we had accelerometers to see, the vibration, because that bridge was suffering a lot of vibration. And you can see that from the modeling that we did and the simulation, the model was telling us that when the truck is going in the adjacent lane, they will probably cause some tension, because it was a floor beam and there's stringers sitting on it. So when the trucks are going in the adjacent lane, the floor beam was rotating. And when it rotates, it kicks the stringers to be in tension. So you can see here, those are the stringers, and those are the floor beam here. So when the floor beam rotates, the stringers on this side will be kicked up, and then causing the fresh concrete to be in tension. And so we followed our model, followed what the model is telling us, and we put the sensors. And lo and behold, we found out that the sensors are behaving, the data from the sensor is showing us that the behavior is exactly what the model is saying. And we also at the same time, so we need to have an information, what is the weight of the trucks that are going by, that making the floor beam rotate. And we can see in the top corner, there's a plot, and there are a lot of trucks that are above 80,000 pounds. I think we circled one here. This is, I apologize, this is a very small figure. And we looked at those the vibrating wire sensors, and you can see that when the crack happens, it happens that we place the sensors zigzag based on the model where the cracks are going to form. And it was found that one of the sensors will pick the crack. You can see here, there's a crack map of what the type of cracks they were forming. And lo and behold, I think the sensor picked up the jump, and we correlated that jump with the time, and we found out that there were 4 trucks, going one after the other as a convoy from a quarry nearby. And that was happening during the 3rd day, okay, after they poured the concrete and while they were doing the burlap curing. And I think the engineers there, they agreed with me that I said, if the cracks are taking place during the curing period, then we can eliminate shrinkage as the culprit. And that's what happened. Then once we found this, the same day we went and we revealed them in front of everyone that the crack is forming here while you are curing. So when we lifted the burlap and waited a couple of hours for the water to dry, you could see the crack exactly where the sensors have predicted that or have shown that there is kind of this anomaly in the behavior. Otherwise, this is a new. I think no designer, no consultant would have predicted this. We didn't even predict it, but the fact that we used WIM and shim to diagnose this problem was a very effective way to prove it otherwise. Another case study that I'm really it's still undergoing, and this is support from our Bridge Resource Program with the New Jersey DOT. This is one of the bridges that we are doing monitoring. The DOT was, concerned that there might be, this type of bridges have been in service for a long time, and they wanted to know, the status of this bridge in terms of what are the loads on it, how is the behavior, coming, if there's any excessive deflections. So we did a combined modeling and shim, and we also at the same time, we input some sensors for long-term measurement, but we also put, on the main 2 right lanes where the main truck traffic is going. These are I think it's 4 lanes. We did also a WIM study, and we found out a very high percentage of overloads that, that are going on that bridge. And at the same time, we were able to correlate the weight, the overweight spectra with what is the fatigue details in that bridge, what is the deflection, impact on that, how the trucks are impacting the bridge. And we were able to correlate the 2 to give a better answer. Okay, and currently we did some ultrasound testing on it just to confirm that the locations are okay. This brings me to the most important work that we're doing right now, in my opinion, and this is the Brooklyn Queen Expressway. It's a test bed in collaboration and huge support from the New York City DOT. They gave us access to put the different kinds of sensors on the bridge. They have subcontractors and their joint venture a consultant were very instrumental in facilitating this work. So we tried to use a new technology, which is the fiber optic sensing, because this is an old concrete structure, and point sensors will give you the stress or the strain, indirectly the stress, but the strain at only point sensor, point location. But we don't know what if there's anything to happen when we do long-term monitoring, you might miss the location of where are the critical hotspots. So with this fiber optic, distributed or continuous sensing, no matter what distress at any point, in the plane, where this fiber optic sensor is crossing, you will be able to get an idea continuously, and this sensor is very rugged. I have to mention this is in collaboration with our partner, structural monitoring solution. This was brought attention to me by our CitoSmart industrial partner, Terry Tamutus, who has huge 25 years of experience in the monitoring, and he instrumented this in a couple of bridges, one in Hawaii, one in Florida, and it has shown to be very, very effective. So I think we borrowed this kind of concept because it really fits the location. Maybe it doesn't measure the strain from every truck, but it gives us an idea, especially for the long term, what are the changes, and if there is any excessive deformation due to any of the so that was one of the new things that because I worked with fiber optic sensors before, but they were not rugged enough for field application. We did work on the lab with it. It has shown to be very helpful, but it didn't really this type of sensor. I'm very happy that we used it because it has even 4 fibers inside of it. So if one of them gets damaged, the others we have redundancy, and one of the fibers is used to measure also the temperature. So we will have better idea. Another point that we did is because this unique structure is a cantilevered structure, the way it was built, we also wanted to know globally what is happening with the, if we monitor the structure for a longer period of time and you have the signature record of it, based on the acceleration, maybe we can detect changes in the different modes that are being recorded right now. So this is something that we are dabbling with right now, and we are trying to develop models to detect, we have a complete finite element model that we are trying to do for the specific spans that we collected. In addition, for this case study, to make sure that the fiber optic sensor, to test it, and to make sure that it can detect minute, changes in the strain, or if there's any crack to be formed, I wanted to know. So we did just finished about, maybe we had about 6, we built some concrete, precast concrete beams in the lab, and we placed the sensors, if you can see it, on the outside surface, the same way we did it, we epoxy it on the BQE. And we did also sensors within the concrete, just to compare if the surface mounted sensor will give us the same strain as if the sensor was embedded inside, and at what strain level does it predict, and what is the noise involved. So we wanted to do a more thorough job in trying to have more confidence in what we are, be collecting in the long term. And the idea here was to, build a way to filter the data. There's a lot of data, and we are getting help from our partner. It's a Spanish company. Javier and Terry are through structural mounting solution. They are the ones that develop the technology, and we are working very closely with them to explain the anomalies and get the data. And for this also, I thought this is kind of the response side. We also, so you want to know if there's anything that the response side is picking. We want to have some correlation with what is the cause of that. In the long term, it might be just the accumulation of damage. However, if there's a big event that would cause that, especially if there's an extremely heavy truck that is, we wanted to know that. So we instrumented a pilot study, again, with the help of the New York City DOT engineers and their subcontractor and partners. We were able to provide our assistance, and they placed the sensors in both directions, 3 lanes each. But in one of the lanes, we wanted to test if you can see this lane here, these are the Kistler sensors, the one that are higher accuracy, to compare their performance with the performance of the other sensors. And on top of that, they also helped us in the last couple of months in putting a camera, and can measure take a picture and the license plate, We put one camera in the front, one camera in the back, so we have more redundancy. And we were able to get excellent accuracy, from those sensors. This is the team, our team putting up the sensor with the help of the Kistler representative, Jess Helblinger and James from Kistler. They were very instrumental in supervising this work. And we started recently collecting data on that. And the system in conjunction with each other, the WIM and the camera are working, but there are some things that we need to figure out. So we're doing right now a lot of the programming to make sure that we don't miss any trucks. And we found out that during the day, we have a lot of good data on to match one-to-one. There are some trucks, for example, that don't have license plate, some trucks that are shifting lanes. So we have to find ways in our programs to really handle these situations. Other than that, everything is working. We believe that this pilot study was very important for another project that New York City DOT will be embarking on. I think our New York City DOT and I, Tanvi Pandya, who's the director of this project, presented at the Commercial Vehicle Safety Association in last August. We presented our work on this one, and this was, to my knowledge, this is the first one in the country that really has gone to this level. And I have to give the DOT, the New York City DOT, credit for them pushing a legislation in the New York State. And we're hoping that the legislation will be signed. It passed the chamber and the assembly, and it's with the governor. We hope that it will be signed soon, because that's the beginning of an era that it will highlight the automated enforcement. So that is our, the part that we wanted to do is that to adopt this, we needed to do a calibration. Unfortunately, ASTM is kind of silent on this type of technology, although it has enforcement, but it does it mainly on the scales for the weigh scales and the WIM stations on the side. There hasn't been a enforcement because I think the US is lacking behind the rest of the world. So we tried, and this is our main contribution here. We tried to bring that technology, but at the same time, we wanted to develop some new standard or append to the ASTM standard the new standard based on what the rest of the world has been doing. So we looked at NIST, which is another American standard. We looked at COST, which is a European standard, and we looked at the international standard, the UML International, which is many countries are using that. So each one calls for a different way of calibration for different accuracies. So we tried to combine the best of everything. And I would like to, and thanks to the DOT, they really went out of their way and to use their in-house fleet. So they reconfigured some of the trucks to basically make them according to what each specification is doing. And some of them call for only 2 trucks, some of them call for 4 trucks. So we tried to cover all 4, and we did the calibration, and now we're up to do another one. So this shows when all the truck fleet going over the locations of the sensors, and I think it's looping now. So this is the all 4 trucks, and you can see there are escorts and for safety. So this was done very successfully. Okay, I think it's looping now. So, but I just want to share with you it is very, very doable. I mean, this is our conclusion at the time. This was done probably, 8 months ago, and now we're doing another calibration on December 4th. So the conclusion there that using these sensors and that location with the pavement as is, without any repaving or just minor, grinding, we were able to get the compliance needed in majority of the specification. So it is doable. I mean, we didn't go that far without knowing that this is very much doable. And now the DOT is really launching a new project on a different location in BQE, which will be fully instrumented with this technology. Now, what does the technology do? Well, it's just a combination of the WIM data and the ALPR camera data. Unlike other sensors, I mean, this has been attempted, but it's mainly hardwired. So we try to do it very efficiently without doing the hardwiring. So the camera will be working in its own, and the WIM system will be working in its own, but we are synchronizing the two. So the effort of programming is very heavy, but that is a much more effective way, which I don't think, maybe others are doing it, but I haven't seen it in the US. So that will help, in a way, minimize the installation and the problems that go when you have hardwiring of the cameras. So this is a project that, there are other countries that have done that. We reviewed that. We looked with the help of Kistler. They have reached to different countries. We've seen it being done there, more sophisticated than what we are doing right now. But I think eventually this is our first site. I think the leadership of the New York City DOT is really forward-looking. And I'm hoping that this will be a success story for the sake of our country, because I think we need to do that. Our infrastructure, as you know, the bill was just recently passed, and we're hoping that this kind of technology will make it a very level playing field for the agencies. Yes, we are for increasing movements of goods and services. We want to facilitate the trucking industry and their contribution to society, but they have to do it within the rules that our infrastructure is not at the point where it can take all kinds of loads. I mean, relatively, especially in the Northeast, and in New York City and in New Jersey, the infrastructure is, the average bridge is 50 years old in New Jersey. We have 6,000 bridges, more than 6,000. So you can see that it's an older infrastructure. It's well maintained, but I think the pace at which it's maintained is not keeping up with the traffic and the loads that are being increased. So I think the automated enforcement is going to be the answer, in my opinion, and that's what CITO Smart has this emphasis on that. And we have a theme, just for the infrastructure resiliency, and we're hoping that our partners, industry and the agencies will they speak the same language right now, and we look forward to a successful conclusion of this testbed. Anyway, I just wanted to list here a lot of the people who are involved in all these projects. I want to thank them again, especially the New York City DOT, and also I don't want to forget, I'm on this side of the river, so the New Jersey DOT, especially the current leadership, is really very keen on supporting this type of work. So I want to thank you all, and I'm sorry I took a little bit of time, but I would like to take any questions if there's any questions.
Yeah, we're actually right on time. So I forgot to announce this in the beginning, but if any audience members have any questions, you can submit them one of two ways. There's the Q&A button at the bottom of the screen, and you can also raise your hand and I'll unmute you and allow you to speak directly to Professor Nassif. I think in the meantime, we've gathered some questions in advance of this presentation, and I also have a couple of my own. So Hani, you mentioned computational storage as a historic bottleneck that we've gotten through that's allowed some of this research to move forward. I was wondering if you could speak more about the present day bottlenecks, technological, financial, or political, that if broken through will push this research forward.
Yeah, it goes without saying, computing is advanced. So I remember when I did my research, I used to carry my XT, to the field, because we didn't, lunchbox was like $7,000 to buy a small, we used to call it lunchbox. So the technology really had a big impact on this field, especially storage. and wireless. Now we have and the compact sensors. I mean, now the MEMS and all these. It's making it very, very simple. Even your iPhone is a you can call it as a sensor. To that event. So in a way, yes, the computing have changed drastically. Especially, I would say, storage and the processing, that you can do things in real time now. Now, I would not have imagined that that the camera and the WIM and all of them can work together. We have a very powerful computer on site which is collecting both data and is displaying it for us in videos and everything in real time. So that really the impediment now, I would say, is that one is political. I would say the politicians are a little bit behind, especially when it comes to infrastructure. I think hopefully this administration understands it and they passed the infrastructure bill as a both effort from all the politicians. So I think we need more of that. And because our infrastructure, if you compare it to other countries, the bridges that suspension bridges, the US was leading the world in that. Now, if you go, we're not anymore. We're not building new type of technologies. We're not reaching the limits on a lot of the use of this. So I think politically, we need legislation. We need support to allow these technologies to be implemented. I think we are at a starting point. The impediment was that nobody has done it. So there's always that there is the need to have a precedence where people did it and it was successful. Now we are trying to iron out the kinks in what we are trying to do. It's an ongoing effort, I would say. We do our part, but I think the main success is really for in our case in the BQE is for the New York City DOT. Their leadership, their engineers, they are the ones who are seeing what we have been seeing, and then they're responding very positively to implementing this type of technologies. So I think the main impediment is the political atmosphere, and the second one is we need to start graduating or teaching civil engineers that are a different breed than what we classically have done, meaning that we dropped electrical circuits from our curriculum. But if you tell the students how a strain gauge would work, you really need to know the basics of how all these sensors, how do they, I'm not saying you have to be PhD in electrical engineering, but we need to understand the technology, the programming side, the new opportunities that are presented to our students. So we need to kind of take from our shell and start looking at how SHIM and WIM can help our civil engineering infrastructure. So those are the two, I would say, major points that we need to do.
Yeah, sure. That was great. Thank you. So we have a question from Thomas. If you could, you mentioned this earlier, but what is the most accurate type of sensor that you've discussed? And maybe
the accuracy, to be honest, if you're looking for 5% on gross vehicle weight, you can get that through the Kistler sensor. You can get it through the more or less through the bending plate, and you can get it through the load cell sensor. So those three sensors are as accurate. Now, sustaining that accuracy for a longer time with minimum amount of maintenance, and that's what we're looking for. I found out from my own research, and other people spoke to that in a different way, that the Kistler sensor, the quartz, are really the porch of the sensors, right? Not because they're expensive, but because they are worth their because they last longer, more than 8 years. There have been some of them 5 to 8 years in different states when we anecdotally asked around, but I think for the ease of use, for the way they set up their sensor with their system, it allows to have APIs to communicate with other types of sensors. That was not in the other systems. Okay, so the sensors are one thing, but also how the data from these sensors go into a box. How do we have access to that box? If I want to put a camera, if I want to put a temperature sensor, if I want to put a clock, if I want to do whatever I want to do, I think with the Kistler sensor, they work with us, and I'm sure the other vendors will also do the same if needed. But I think this is, from my experience, and in this project, we're seeing it, that the Kistler sensors are really the best.
Okay, thanks for your question, Thomas.
Hani, this is Khan Asbe. So I want to ask Hani, and it's I mean, not a softball, but I just, because this is something that we discuss always. I mean, these are great technologies, and I know you've been working on this for a very long time, okay? But I mean, being a transportation person, I learned a lot from you about this. But one thing that I'm curious, I mean, and the government, even the federal government, tried to invest a lot of resources on this. But every time we go to a project together, I mean, I'm on the traffic side, I don't use these technologies I don't see these technologies being used the way I hope they'll be. I mean, they have to be mainstream now, you know?
Yeah.
I mean, of course, you're doing research and you're doing different things. I mean, you kind of compare lab work with the field work and so on. But I would expect, after all these years of work, and this is a lot of years, I mean, not only by you, but there are other researchers, why this is not more mainstream? Why WIM, for example, is only limited to what the Federal Highway defines to collect this data and report it, but not these more mainstream usages of these technologies are not out there. I mean, do you have any? I mean,
yeah, I think you know, this is Khan, you and I talk about something like that, because whenever we did a project, we always found a way to combine what you do and what I do, and using the same sensors for the holistic approach, right? So that makes it much easier. But I think there is the reason you and I talk is that's the reason why we find out about what are the needs for your projects and what are the needs for mine. And then we see that, okay, there is a lot of commonality. I mean, the way a motion sensor, they're not only for weights. I mean, it can measure traffic speed, it can measure, you know, at time, so you can get that traffic density. It's a traffic sensor. It's a counter, it's a lot of things. So unfortunately, the dual use of those sensors has not been, it's compartmentalized in a way that everybody does that sensor for their purpose. But there hasn't been the communication between different disciplines has not been done at a level that is encouraged. So, you know, for example, I think, you know, in my opinion, there should be a cross-discipline, you know, especially people who develop the sensors, people who are end users, people who fuse these sensors together, people who collect the data. There should be a setup where all these people can be in one room in a way. And that's happening, but in very limited basis. I mean, if you go to NSF, you know, they don't have a lot of this multidisciplinary type of, it's in one field, and it's civil engineering or electrical engineering, but across discipline, we haven't been able successfully, you know, although some people cater to that, but it's not really, spread in a big way. I think maybe this could be a federal highway initiative where to bring in a different application, especially now in traffic. You know, connected vehicles are mainly a invention that electrical engineers probably are working, or computer scientists. You know, but many times when they talk to a traffic person, they find out that what they're doing is not really applicable, you know, because of the traffic, you know, rules and laws and how you can manage things. So I think the communication is number one needed. I think, for example, the C2 Smart role, we've been trying to do that. I know from the webinars and from, you know, we're trying to fuse these different disciplines together. But I think the pot of money that an agency like DOT, for example, that is allocated for this type of vision or for this type of work is very, very limited. They can barely have enough funding to keep their operation going. And that's at the local level. So money at the local level has been, there's no money for multidisciplinary, approaches. So I think you know, in a way, I don't know if I covered everything, but this is something that, you know, we need to press more to speak to other computer science, you know, electrical engineers, even some psychology. I know in your field, you know, you need to understand the behavior. You know, how is there compliance or not? And
I was thinking about economists because
yes,
we really, need to show the value of these sensors, what we can save. As you said, the budgets are tight. But if you can show that you can save a lot of money by doing effective monitoring and turning that into actionable item for the DOT, for their maintenance, for their replacement, I think that will save money. And actually, the money that's spent to deploy these technologies will be relatively less compared to what can be saved. So I mean, I have a feeling that some things are being done, and not only, I'm not talking about New York or New Jersey, all over the country, without getting all the benefits of these sensors to make smarter and more effective decisions, maybe to delay or to kind of do the early on, so that the structure doesn't like come apart. So I think these technologies, they have so many roles that they can play, of course, combined with smart algorithms and smart decision making. I think decision making is key here. I think that's what's missing. I think
I agree with
data is
you.
being collected, but decision making part is still not there. I mean, that's my
I think, and that's the lack on maybe on our side. My approach, I mean, when people say structural health monitoring, the first thing they think about is sensors and where you put them. But I think, in my opinion, that's not what we, what we do actually, is that we found out from our experience with different agencies, and the reason they allow us to do this is that we close the circle. You collect, the data, you process the data, but then you collect the data for 1 month or 1 year. How do you predict what's going to happen to the bridge in 75 years? So you need to have some prediction models, and the prediction models, they cannot be deterministic because the nature of this data changes every day. And even if it's a traffic, or if it's loads, or if it's sensors collecting strains, the data is going to change. So how do you predict, to best your ability, what the future is going to look like? So you need to have some probabilistic prediction techniques, some statistical methods to filter out bad data from good data. So I agree with you, especially the economic side of it. When you do something and you show that you could save the agency a little bit of their budget because the prediction is validated over time, then that can be a reliable model to be able to use it more quantitatively.
So we have two questions.
I think, just one last comment. We could call it like operationalizing the data, decision making with data. So basically making sure that the data is not just data sitting in a big computer, but it's being used. And I think that's the part that's really missing in this the whole thing. And a lot of people are saying we have all these whims, but other than reporting the weights, how are we using this data? I think your research is a great example of like showing how it can be used. I think that is the
and I don't want to oversell this. I think, when we say about prediction, I'm not going to predict. We try, but it's a guiding, it might not be, my PhD advisor always told me, that we're not telling the absolute truths, but we're telling the least lies, right? That's so we're trying to predict within a domain of confidence or an interval of confidence to help the direction. It cannot be like flipping a coin or looking at it deterministically. So yes, these methods, if you don't supplement them with a model or with an approach that can give you an idea, then it's not very useful to the agencies. And that's what they're looking for,
So in our last minute here, Charles, I apologize. I'll read your question, but I'm going to breeze through the other two questions here. So Charles just wanted to share that Professor Nassif, your idea of a multidisciplinary team and as an approach to WIM is one that New York City DOT is taking with their team that includes traffic planners, economists, as well as bridge engineers. So thank you, Charles. We have time maybe for one last question here, which is if you could just speak very briefly about your validation efforts to cross-check the number of vehicles in a specific lane for a specific period of time and compare it with the data that you gather.
Right. This has been underway. We did it a couple of times. What we have noticed, for example, and that's a good question because that speaks to the what we're trying to do. So we have now one lane, and we directed the camera on one lane. So we did 5 minutes of intervals, and every 5 minutes you get about maybe 200 trucks or so, or 100 trucks. So we tried to see how effective that matching algorithm that we have. And so there are some issues. For example, there are some trucks that don't even have license plate. So you get their weight, but you get, the system that gets the license plate will not take an image unless there's a license plate that can capture. So that's some of those trucks, we are not able to, we see them, we get the weight, but we are not able to manage. There are some trucks that when they are close to the wind, they shift. So they press on one sensor, but they don't go over the other sensor. So although we have their license plate, but we don't have their WIM, data. So, and we also, in this pilot study, we focused the camera in one lane where we have the sensors only. Normally, the camera would have a wider field of vision. So it will pick other, so even if the truck shifts the lane, we will still get the license plate of that camera if we direct the camera to give it the whole field rather than only the lane. We did it this way just to measure how accurate it is. I think the effort is underway. I would say we had about during the day, it was different during the night because the location we have, there's a minimum amount of light. The cameras, they are very sensitive to even small amount of light. So they pick up license plate at night, but we need to have probably proper lighting to get a higher percentage. So during the day, I don't want to quote the percentages, but if we take out all these events, for example, some trucks have license plate on the front, but in the back, they have a different license plate. So we try to do the back camera to confirm that because the trailer might have a different state or different license plate on that one. So we are working through that, but the efficiency of that was very high. Even with those, if we take them out, we were, above 90%, I would say, matching. So we are doing it. We are changing the programming to take into account these different things, and we are improving it. And when we check it with manually, the results are very, very promising. But at night we have less. So we need to figure out the light. The camera themselves, they emit some light, but the reflection sometimes, the angle of the camera, might not be the right angle. So one of the things that we're thinking about is to have a camera with a swivel so we can adjust instead of closing traffic and all of that, we can adjust the camera from a distance, so this way to have the right angle for the front and the back. So I think it's very good. I think New York City DOT allowing us to do that and doing that ahead of everything else, I think it's the most beneficial in my opinion, because now we know how much we are missing and why. And for example, we were thinking when the shifting lane, maybe we should make two-striped lane, two-striped lines so that you're not allowed to shift lanes. So when they shift lanes, it becomes a violation itself because, of course, some of the truck drivers, they will know that and they will try to do that. In other countries, when I was in South Korea and sabbatical, they told me exactly that. They put additional sensors at 45 degrees to avoid doing that. We don't want to make it that complicated because the ones that we are missing are very few anyway, right? So this is one of the ideas that are coming out from there. So I think we have a good compliance. Good matching results so far. It's above 90%.
John, there's one question I want to answer. I saw it in the, so I'm going to apologize.
Yeah, we need to answer all these later on. Maybe.
Yeah.
The question about sensor information should be in real time and there are bandwidth issues and cost issues. That's not true for most of the data that we collect today. Most of the data we collect today is, especially WIM data and so on, it's light data. So there's no bandwidth issues with that data. There's no cost issues with that data. Of course, if you want to bring real live video data, that's a problem, not so much the cost, but bandwidth maybe. But even that one can be handled because you can do edge computing and you don't have to download and put everything in the cloud. No, you can basically do things in situ, but every other data, we solved that problem when I was doing the fog sensors for New Jersey 20 years ago. There is no cost issue. There is no bandwidth issue for most of the data we collect because text data. So it's not that it's not a problem. So we can bring all the data in real time.
Yeah.
So
And before we close, Khan, if you ended, I would like to announce that we will be, through the Bridge Resource Program and with the help of C2 Smart, we are developing for those who are interested in the design side of it, we are developing a course, probably first time we'll do it is for NJDOT in-house, but at some point we will also have a training in the structural health monitoring and WIM. We did that in one summer, but we will bring it back. It will be announced soon. We'll let everybody know how to apply it in pavement, how to apply it in bridges. So we will have a short course, maybe a webinar will introduce that, but the course will be maybe a 1 or 2 day course in the future.
Okay.
that's great. Thank you, Hani.
Thank you very much. And with that, I just want to thank everyone for their questions. They were all great questions. And thank you, Professor Nassif, for giving us the state of the field of WIM and structural health monitoring. I hope you all will join us next time. Have a wonderful break, and we'll rejoin in December.
Thank you. Have a good day.
Take care, everyone.
Bye-bye.